I'm Mike. I work at a company named Thoughtbot. We are a web mobile consultancy. I run the Swedish branch. We are hiring, as is every other company. This is a talk about object-oriented programming, what it is and when not to use it. It is applicable to both Python and Ruby. Who here is a Ruby developer? Awesome. That's a lot of you. Who here is a Python developer? Okay, hi. All these slides are in Ruby. And last night I started translating them to Python, and I realized that all I was doing was deleting some things. So I'm sure you can understand it. So in order to talk about when not to use object-oriented programming, we first must discuss what object-oriented programming is. So I think of programming languages as this kind of scale from OO to functional to whatever's in the middle. And you got like Smalltalk, and that's object-oriented programming. And you got Haskell, and that's very clearly functional programming. And then you have this kind of stuff in the middle. And really, it's kind of a circle, right? They kind of connect, they kind of get closer together as they get more functional and pure in that sense. I think they're kind of tied together. Does this fit? Yeah. I think they're kind of tied together. We can talk about that later. So object-oriented programming, according to some definitions, is closures, polymorphism, and Liskov substitution principles. So those are some buzzwords. And by the end of this talk, we will probably have an understanding of what that really means. So what is not object-oriented programming? That's what I'm going to talk about. So aspects. Am I talking too quickly? I'm a native English speaker. Is this fine? OK, great. Aspects is an example of non-OO. This is the idea of cross-cutting concerns, grouping them together. So I'll show an example that does not use aspects. This fits. OK, cool. Can people read this? How am I doing? Great. So here we have the classic object-oriented transferring data between bank accounts example. You check whether the user has access. Then you make sure there's a transaction, and then you withdraw and deposit, right? And otherwise, you handle some exceptions. The problem is that this transfer method is responsible for checking access, doing the transaction, and actually doing the transfer. Right, so in terms of single responsibility, this method doesn't have it. So we can split it out. We can have sort of aspects. So we can have this transfer method that does exactly what we need. And we can say around, before do this, and around the transfer do a transaction. The actual details of the code is not that important. This is probably using some active support stuff from Rails. Either way, this is possible, but it doesn't get all the way there, because now account is responsible for the transaction, the permission, and the actually doing the transaction. In terms of single responsibility, this object doesn't have it. The downsides to that, of course, is that it's harder to test, harder to reason about, harder to think about. So we can split it out, and we can say, here is a transfer method on an object called account. It does the transfer. We can say, we can have an account accessor that checks whether the account has access to the second account. And we can have a transactions class that wraps something in a transaction. So now we have these separate components. We can glue them together with this, what do I call it, connect aspects class. So we can have these aspects as a separate component that glues things together. The benefits, we had put all the behavior in separate places. They're testable individual pieces, and we can glue them together with a small bit of glue code. This is totally possible within Ruby, within Python. Here are some Ruby gems, facets, aquarium, and aspector that make this possible. For more details on aspects, you can read up on the guy Karl Lieberher from Northeastern University in Boston. And some of you who use Rails will recognize that aspects are how Rails does callbacks. Right? So this is not object-oriented programming, and it's totally possible within our language, and it has benefits. So let's look at another example, functional programming, something I particularly love. This is where you concentrate on behavior instead of data. So here is not an example of functional programming. Here we rely on polymorphism, and so we have this number system that we're representing in Ruby. We have addition, and it takes some list of operands, and it evaluates all the operands and then sums them together. And then numbers, that's one example operand. And the evaluation of a number is just that number. And I provide a little example of how to use that. You can add the addition of two numbers with another two numbers. Right. So this is object-oriented programming. This is a classic example of it. The problem is that as the number of classes grow, it becomes harder to add new behavior. So we had addition and numbers. If we add division and subtraction and negation, so that's fine. We can add all of those data structures and provide an evaluate method. But as soon as we add an inspect or a simplify or evaluate and show work, we now need to modify all of these classes, all spread across the file system. An alternative is a functional style. We have data structures instead of classes that just store the data. And then the evaluate method turns into an evaluate function that takes the expression and does a dispatch on it. Right? So this is a manual dispatch. This is what object-oriented programmers avoid when doing OO. But this means that we can now add more behavior. We can add a simplify function without modifying any existing code at all. We don't have to look across the file system for files or anything. We can just add a function and have it exist. So this is functional programming in summary, where you filter and operate on data, on structures of data. So instead of adding behavior to data, you are adding behavior to the system, and data is passed to that. And this provides behavior as first-class objects. Obviously, more places to look and read about this is Haskell or Scheme. The book A Little Java, A Few Patterns teaches Java in a functional programming style. Functional Objects was a talk by Matthias Fleisen, who I think also wrote A Little Java, A Few Patterns from eCoop a bunch of years back that explores this more. So another non-OO, structured programming, where you use the language keywords, where the language itself has to support the structure of what you're trying to represent. Conditionals are a common example of this. So here's an example that is not structured programming, necessarily. This is just using polymorphism. We have these users. It could be a user, an admin, or a visitor. And they all respond to name and produce different results. Some of them inherit from each other, or all of them, and we'll call the superclass. The problem, that's a lot of code just to show the user's name. We sometimes see this complaint on Twitter from DHH of Rails fame. Sometimes it is a valid complaint. It never is when DHH complains, but sometimes it's a valid complaint. So here's and this is actually very similar to the functional style, where you use the case and the use the case syntax to split apart the data structure. Right. So this is very similar to the functional style, but here we're concentrating on the fact that we're examining we're using syntax in the language instead of using methods and defining our own syntax. Here's another example of where structured programming is handy. This is not structured programming, necessarily, where we have a list, and it's either an empty list, and the length of the empty list is 0, or here I did a tail call implementation, but the length of the empty list is 0. Or we have a linked list, where the length of a linked list is 1 plus the length of the tail. Right, so this is the natural recursion. You could write this using inject. But the problem is that tail calls are not optimized in Ruby or Python. Is that correct? Yes. OK. Tail calls are not optimized. Blows my mind, but they're not optimized. So this code is going to blow the stack if you have a long list. So this is a really classic example of structured programming, where you have while loops and imperative programming, where you're incrementing a number and you're checking whether something is a something. Now, this is faster. Sometimes it's more readable, sometimes not. Sometimes it's more concise, sometimes not. Sometimes you have to work around bugs in the language. Sometimes it's faster. So that's structured programming. Sometimes it makes sense to do this. Obviously, for more places to read about structured programming, Java is definitely not an OO language. That's a good place to look. And The Art of Computer Programming is a fantastic read in general. Very related to that is imperative programming. And so here is, again, not imperative programming. We have the gigawatts, and we have to know whether we have enough gigawatts. Well, we can do an inject of addition over the collection of gigawatt and see if we have enough. We need, what, 121? 1.21 gigawatts, 121 gigawatts. Yeah, seems right. For you Python people, inject is how we spell reduce. The problem is that this has to be fast. We have to very quickly discover whether we have enough gigawatts. Time is of the essence. So we can rewrite it imperatively. Again, this is structured programming. And so I'll show another example of imperative programming, where, so here we have Gherkin, which is the language used by Cucumber and a few other tools. There's definitely a Python tool for this. I forgot its name, though. Where you can write your tests in a natural language, and it's a step-by-step iteration. You can't swap the steps and have it make sense. You read top to bottom, left to right, and this is how the code goes. So that's imperative. Sometimes the algorithms are naturally imperative. So Gherkin is an example where the algorithm you're expressing there is an imperative algorithm. Sometimes it's faster or easier to optimize. Sometimes imperative programming makes sense in the middle of your object-oriented code. Obviously, a great place to read more about this is C, and the C programming language is a fantastic read. In fact, that's a fantastic book. I recommend reading this book if you haven't. So Gherkin is a good example of language-oriented programming, where you make a domain-specific language that's expressed in the domain or in terms of what you're trying to solve. In Rails, we have the routing. This is a tiny Ruby domain-specific language. Gherkin is an example I just showed. RSpec is another example where, this is normal Ruby, but it reads very much in the language of what I'm trying to express instead of test unit, which is defining methods and naming the methods specially. A bigger example of domain-specific languages comes from Scheme, where you can define syntax in the language itself. So here we added a conditional that doesn't have an else clause called when. Obviously, we have this already in Ruby and Python, but this is an example of in Scheme, we can define conditionals as part of a programming scheme. That's a level above what we have. So language-oriented programming, where the problem is best expressed in the domain of what you're trying to say. And you think in terms of the algorithms instead of the objects. Again, this makes sense in a large app. We have object-oriented programming going on. Sometimes you need to break out into the domain. If you're doing Ruby, parselet, Ruby to Ruby, and Ruby macros are some gems to look into. If you're doing Python, a quick search for Python DSL revealed a whole slew of information. So that's cool. So this is the last example I'd like to talk about, and this is logic programming, where this is a domain-specific language that is describing the problem and letting the computer discover the solution itself. So here's an example not using logic programming, where we need to print out A, B, and C, where A squared plus B squared is C squared. And we guessed that A must be 3, and then B, we did some trial and error, and we got it to be 4, and then C is very clearly the square root of A squared plus B squared. This is a mess, right? This is a nightmare. I don't know if you can see the blue, but we have comments in the code to describe that we're confused about what's going on. I hate comments in code, so that's a problem. Right, so the problem is that there's lots of guesswork and computation that I have to do as the programmer. This means it's brittle to change, it's hard to test, I don't know what's going on. Another way to express it is to use an ambiguous variable. So it'll say A, B, and C are ambiguously 1 through 17. Doesn't matter, I just know it's in that range. We set up a guard saying that A squared plus B squared must be equal to C squared. And then when we print out A, B, C, we get the correct value. Here, I'll show you. So here is the file logic Pythagoras. Can we see this? Yes, great. OK. And it's just what we were just looking at. This is Ruby. And so I've loaded the Ruby interpreter. And I'm going to load the logic Pythagoras. And it should print out ABC and prints out 3, 4, 5. Hey, how am I doing on time person? OK, great. I'm doing well on time. Thank you. I'm going to show you how this works in the back end, because this is really cool. First, actually, I was a little confused about this. Does Python give you access to first-class continuations? Yes? No? OK, cool. I do not know either. So in this, in logic Pythagoras, we have choose. And we say A is a choose of 1 through 17. And then we have guard. And guard sets up a rule saying that A squared plus B squared must be C squared. So what we pass to guard is a Boolean. And what we pass to choose is an enumerable. So the first thing we do is we set up a failure stack. That's this global thing that is a stack of, well, we will see, but it is a stack of places to go back to when we failed. So choose takes a list. We make sure it's a list. We grab the current continuation. So the current continuation is, as we're evaluating the program, the place where we are right now is the current continuation. And if we were to save that away and then come back to it, we would be back there. This is the time travel thing. The time travel, there's a word for it. Whenever you get back to this line, whenever you invoke this continuation, you get back here. And so we grab that. And if the list of choices is empty, we fail. And I'll show what failure looks like, but we fail. Otherwise, we shift off from the list, right? So we have this list, and we pull off from the, shift is the front. We pull off from the front and say, this is our choice. And we have this failure stack. And what we do is we unshift, so we push onto the front the continuation. So now this failure stack is a stack of continuations. And we return the choice at the end, because the choice was the correct thing. But we set up this guard, and it takes a condition. And if the condition is true, that's fine. We'll just produce that. But if the condition is false, then we have to fail. So failure looks like this. If the fail stack is empty, then we have nothing left to do. We don't know how else to go through this continuation. We're out of continuations, in fact. So we fail. We raise. We say we're exhausted. We ourselves are exhausted. Otherwise, we shift off from the stack, and this is the backtrack point, and then we invoke it. It's just, we treat it like a regular function. We call it. And we say, jump back to where you were. And where you were was here. But at this point, we have shifted off the choice. So we just go through and pick the next choice. And we push that continuation on, the new continuation onto the stack. And we keep going until we're exhausted. And finally, we get 3, 4, 5. So, got it? I'll show you a link for more. Logic programming is where you tell the computer the problem, not the solution. And this is useful both for quick calculations, just like, oh, I need to figure out this triangle, what calculation is right. It's also useful for end users. This kind of domain-specific language where like Mathematica and things like that can solve this for you is very useful for non-programmers who are definitely programmers. More about this can be read. So in Ruby, we have the AMB gem, which is the ambiguous operator gem. It provides choose and guard and things like that, so you don't have to write yourself. And AMB is covered in more depth in the book, Structure and Interpretation of Computer Programs, which is like the nerdiest thing to call a book. Let me push my glasses up. which was the MIT intro course for many decades until like 2 years ago. It's a really fantastic read. So that brings us back to object-oriented programming. Oh, I have a thingamajig. Object-oriented programming, we saw, lets us quickly add new data. It encapsulates state so that it doesn't leak out into the ways that we were doing it imperatively. It simplifies the conditionals. Instead of writing a case statement, we just define methods that have the same name. And it builds reusable components without brittleness. But sometimes it doesn't make sense. Thank you. Since you sat through this, here's a coupon code to workshops and online courses. I'm Mike. How much time? OK. I have time for questions. Yes?
So I saw Ruby CC, and you had a comment at the top that said this only works from 1.8. I assumed that was the keyword that was removed from 1.9. Do you know why?
OK. So he asked about this comment that the ambiguous definition I implemented only works in Ruby 1.8. So I do not know why. I do know that first-class continuations were moved out of Ruby in Ruby 1.9. But even if you require them, so you can require, require continuation, I think? Was it? OK. It still does not work. And I did not debug why. I don't have good visibility into Ruby's continuation stack. Yeah. But thanks. Any other questions? Yes?
You mentioned aspect-oriented programming. What are the benefits of it? I didn't get it.
Right. So his question is why aspect-oriented programming? So the benefit of it, in fact, So the benefit of it is that instead of having one method do everything, you can pull that out into separate methods. And instead of having one class do everything, you can pull that out into separate classes. And now you can test these individual pieces as separate components. And glue them together as differently as you want. So I showed the example of a transaction and checking permissions and also doing the actual transfer of money. Those can be 3 separate discrete components worked on by different developers, stored in different code bases, and now you can glue them together as aspects. And the glue code can be separate as well. So that's the benefit, is keeping things separate and testable. All right. Well, I'll be around if you want to chat more. Thank you.